In section 5.4, we're going to be looking at modeling and optimization. By modeling, what we're talking about is we're going to take a real-world problem and we're going to create a function to go with it or an equation to represent that. By optimization, then, we want to maximize or minimize some value related to that equation. So with these, first of all, we're going to have to understand the problem. We want to read it carefully, make sure you identify what you have and what you're going to need. Then we're going to develop a mathematical model, which probably would involve drawing pictures, labeling the parts. We want to introduce a variable to represent what we want to maximize or minimize, and using that variable we're going to write a function to find those extreme values for the information that we're looking for. Then we're going to graph that function, find the domain of it. Domain is important in these problems because the domain often has to do with the real-world application rather than the equation itself. There might be values that fit into our equation that don't actually make sense in the real-world problem. So we have to figure out which variables make sense in the real-world context. Then we're going to identify the critical points and the endpoints so that we can maximize or minimize using everything we've learned about y prime, y double prime, and so on. Then we're going to solve the mathematical model. And if we're not sure, we can check our results maybe using another method, maybe looking at the graph of the original function. And then finally, we're going to interpret the function, make sure that we give units, and decide if the result actually makes sense, again, considering the real-world application of that. In our first problem, we're looking for two numbers whose sum is 20 and whose product is as large as possible. Now the first thing I want to recognize is what I'm trying to find the maximum or minimum of. We want as large as possible, so what we're trying to maximize is the product. So if I'm looking for two numbers, we could say that the product is equal to xy, two numbers. We also want the sum of those two numbers to be 20. So here I've created a couple equations to represent this problem, and I want to maximize this. Now the problem here is I have too many variables in this, but that's okay because I have two equations going together. If I solve this one for y and plug that in for my profit, I can write my equation in terms of x. Now that I have that equation, I want to optimize it. So we're going to look at the derivative of this, and from that derivative we want to set that equal to 0, leaving us with x equals 10. Now we want to check, this is a critical point, but we have to make sure that it's actually the maximum. Now I do have a graph over here to compare it to, but there's a couple tests that we could use. I'm going to use the second derivative test. So we know that my only critical point here is at x equals 10. We found that f prime at 10 is 0. Using the second derivative test then, now I do need my second derivative, should change these to p. My second derivative then would be -2. Now using that -2, I recognize that this is negative, telling me that I'm concave down at that point, which means that this 0 here would have to be a maximum. Now that was the second derivative test. We could also use the first derivative test. It doesn't really matter, whatever's more convenient. And then we could have just looked at p prime. We would have plugged in the number 10 where we got 0, and then we would look for the sign on either side of that. So looking back at my first derivative here, if I had plugged in something less than 10, we would have got a positive number. On this side we got a negative number, which means we're increasing, decreasing. That also would tell us that the 10 is a maximum value. So we also want to interpret our answer here, and we wanted to know the two numbers. So the two numbers are 10 and so 10 plus 10 would give me 20, so the other number is also 10. In the next problem, we're asked to put a rectangle, it says inscribed under one arch of the sine curve. So if we're looking at this graph here, this arch here is y equals sine of x. And we want to find basically the dimensions of the rectangle that will give us the maximum area. Now to do that, we're just going to choose any value x. We're looking for what value of x would maximize this area. And if I want to find this value over here, because I'm looking for the base of this, I'm looking for area, we want base times height, but we need to know the base and the height. So to find this over here, we need to recognize that sine of x would be symmetrical here. So if I'm looking for this value, we know that the sine curve would end over at pi. This would also have a length of x because this has a length of x, meaning that this value here would have to be pi minus x. Now that's where they're getting the length of the rectangle here as pi minus 2x. Okay, because basically the whole thing is pi. We're taking away this x to get the length of our base. To get the height of this rectangle then, notice it's just going up to the curve, which means whatever our value of x is, it would be y equals sine of x, and so that sine of x is the height of our rectangle. The area of the rectangle then is just pi minus 2x sine x, base times height. The next thing we're going to need to do is take the derivative of this. And the derivative will be a little bit complicated if we're going to set this equal to 0 and solve it. The book tells us we can't really do this using algebraic methods, and so what they suggest is using the graph of this, use our calculator to find the 0. We're looking for the 0. Here's our critical point at x equals 7.104. We could look at the graph of the function for area and also find the maximum there, but are we allowed to do this if we're trying to justify using calculus? Well, we need to justify our answer using calculus, so we need to use the derivative, set it equal to 0, and this would be the valid way to solve this. Now looking at this is a positive value for the derivative, a negative value for the derivative, so we are increasing and then we're decreasing. This would have to be a maximum value. Now the question actually asks what are the dimensions of this rectangle, so our dimensions would give us x equals 0.710, and then we would also need the y value. And this is where we would come back to this over here. We could plug in that x into our area here, or we can look at our graph. What we have here, y is 1.122. Remember, give your answers to 3 decimal places.